Now we're going to turn to aspects of inverse functions that are more centered on calculus, such as problems of continuity or differentiability, how you calculate the derivative. And to start with, I'm going to go back to what we have established in the previous video regarding the graph of the inverse function of a one-to-one function if we know the graph of f. So namely that if f is a one-to-one function, then the graph of f inverse is obtained from the graph of f by reflection about the line y equal x. So in particular, that means that if f is a continuous function, that is also one-to-one, geometrically that means that in the graph of f you have no gap, no jump, no hole, and so by reflection about a line, the graph that we're going to obtain is going to again have no gap, no hole, no jump. So this is a little bit of a waving end argument. We could do better and prove that more carefully, but I think the geometric argument is convincing enough that if f is one-to-one and continuous on a certain interval, then the inverse function is continuous on the corresponding interval for the definition. Remember that if f goes from an interval I to its range f of I, then of course the inverse function goes from the range of f of I, to I. So f inverse is continuous on f of I. In other words, wherever it's defined. Now on the other hand, if we're talking about differentiability, remember that a function is differentiable at a certain point if geometrically it has a non-vertical tangent line at that particular point, and the slope of that tangent line is a derivative number. So if f is differentiable at a on our picture, then we have a tangent line, and we can consider the reflection of that tangent line about y equal x, and it's going to be the tangent line to the reflected graph, in other words, the graph of f inverse. So no problem, if f is differentiable, f inverse is going to be differentiable, except that if we have an horizontal tangent to the graph of f, then in the reflection about y equal x, it's going to become a vertical line. And if we have a vertical line, that corresponds to essentially infinite slope, in other words, a limit that defines the derivative number does not exist. So a vertical tangent corresponds to a point where the function is non-differentiable. So f inverse is going to be differentiable as long as we're looking at a point where on the other side, on the graph of f, we don't have a horizontal tangent. So let's try to make that more precise. So we know that continuity is preserved by this reflection process, and therefore if f is continuous, f inverse is continuous. And regarding differentiability, if the function f is one-to-one and differentiable at a certain point b, that I'm going to write as the inverse image of a, and the derivative of f at b is non-zero, in other words, at that point b, the graph of f does not have an horizontal tangent, then f inverse is differentiable at a, and the derivative of f inverse at a is given by the reciprocal of the derivative of f at b. So let's try to see why that is true. We're trying to see if f inverse has a derivative at a and calculate this derivative at a. So we're going to start with the definition of the derivative of f inverse at a. In other words, it is the limit as x is approaching a of f inverse of x minus f inverse of a divided by x minus a. We're going to introduce some notation. F inverse of x, I'm going to call that y. And of course, because we are in the situation where f inverse is really the inverse function of f, that means that f of y is x. Now, we already have introduced in the statement of the result the notation that b is f inverse of a, which I can rewrite as f of b is a. So using this notation in my quotient, I get the limit as x is approaching a of y minus b, because I can replace f inverse of x by y and f inverse of a by b. And then I divide by f of y minus f of b, because x is f of y and a is f of b. Now here we have a little bit of a problem because we have an expression that depends on y and b, but we look at a limit as x is approaching a. But this is not too much of a problem, because if x is approaching a, then because the function f is differentiable, it's in particular continuous, and therefore the inverse function is also continuous. So if x is approaching a, f inverse of x is approaching f inverse of a by continuity of f inverse. But f inverse of x is nothing but y, and f inverse of a is nothing but b. Therefore, we have that if x is approaching a, y is approaching b. So we can rewrite this as the limit as y is approaching b of y minus b over f of y minus f of b, which is really just the reciprocal of f of y minus f of b divided by y minus b. The reason we write it that way is because now at the denominator we have the difference quotient whose limit as y is approaching b is defining the derivative of f at b. Now, because we have assumed that the limit of f of y minus f of b over y minus b as y approaches b, which is f prime of b, is not 0, then we have that the limit of a quotient is a quotient of the limits, and we obtain just 1 over the derivative of f at b, and of course b being f inverse of a, we obtain the formula that we wanted to establish. So we have this general result, and let me try to rephrase it, just give an alternative set of notations and reformulate that in differential notations. So we are in the situation where for the choice of variables, we picked x on the side of f inverse and y on the side of f. So we have y is f inverse of x, which means x is f of y. And we want to calculate the derivative of f inverse. So because y is f inverse of x, that's dy over dx. And applying the formula we just have established, this is 1 over f prime of f inverse of x. And you see that now x is a function of y, and namely it is f of y. So I can differentiate x with respect to y. That's the rate of change of x with respect to y, dx over dy. That's f prime of y. But y here is f inverse of x. So that means we obtain that dx over dy is f inverse of, f prime of f inverse of x, which is exactly what we have at the denominator here. In other words, dy over dx is 1 over dx over dy. So you see that the formula we have in the theorem can be reformulated in those terms, which are easy to remember because it's just taking the reciprocal of the fraction. Now let's look at an example to apply this formula. We consider the function x to the fifth minus x cubed plus 2x. And first we want to justify that it's 1 to 1. And once we've done that, we want to find the derivative of the inverse function at 2. The derivative of this function, well, why do I consider the derivative? Because we know that if a function is monotone on an interval, then it is 1 to 1 on this interval. So one way to justify that it's 1 to 1 is to show that it's either increasing on its domain or decreasing on its domain. So that's why I'm looking at the derivative, which in this case is 5x to the fourth minus 3x squared plus 2. It's not a quadratic function, but it is quadratic in form. Namely, it is 5u squared minus 3u plus 2 if I set u to be x squared. So now we are interested in the sign of f prime, in other words, in the sign of the quadratic function 5u squared minus 3u plus 2. But the sign of a quadratic function is easy to find, and first we need to find the zeros to see if it changes sign. So if we look for the solutions to 5u squared minus 3u plus 2 equals 0, we use a quadratic formula, and in the quadratic formula, remember that you have this expression b squared minus 4ac that you plug inside the square root. If this is negative, you cannot plug it inside the square root, and that means you have no real solutions. In this case, b squared is 9, and if I subtract 4ac, I'm subtracting 4 times 2 times 5, get negative 31, I get something negative. That means there is no solution to f prime of x equals 0. And moreover, you see that f prime of 0 is 2, right? Because if I plug 0 in 5x to the fourth minus 3x squared plus 2, I get 2. In other words, it is positive somewhere, never takes a value 0, and it's a polynomial, therefore it's continuous. That means it is strictly positive everywhere. Therefore, the function f is increasing on its domain, which means that it is, in particular, 1-to-1. Now back to the question of the derivative. Now if we apply the formula we just have seen, the derivative of the inverse function of f at 2 is simply the reciprocal of the derivative of f at f inverse of 2. So what we need to find here is, we've already found f prime, we need to find f inverse of 2. And we can observe that f of 1 is 2, right? If I plug 1 in the original function f, I get 1 to the 5th minus 1 cubed, that's 0, plus 2 times 1, so I get 2. Well, that's just an observation that f of 1 is 2, and that means that f inverse of 2 is 1. In other words, the derivative of f inverse at 2 is a reciprocal of the derivative of f at 1. But we've already calculated the derivative of f to be 5x to the fourth minus 3x squared plus 2. So I plug x equal 1 in this. I get 5 minus 3, 2 plus 2, 4. So I get the reciprocal of 4, 1/4 for this derivative. Let's look at another example. We have the function square root of x minus 2. And first we want to show that it is 1-to-1. Again, we can use the criterion that if a function is monotone on its domain, while on an interval, then the function is 1-to-1 on that interval. The domain of f here is all the real numbers greater or equal to 2, because we want x minus 2 to be a non-negative number in order to be able to plug it inside the square root. The derivative of f, f is x minus 2 to the 1/2, so when we differentiate we get 1/2 x minus 2 to the negative 1/2, in other words 1 over 2 square root of x minus 2, and that is positive as long as it's defined, that is for x strictly greater than 2. That means that f is increasing on the open interval to infinity, and in particular it is 1-to-1 on its domain. So now that we know that it's 1-to-1, we may want to calculate the derivative of the inverse function, for instance at 2. How do we do that? Well, we have a formula that I remind you here. And in our case, a is 2, so the derivative of the inverse function at 2 is just a reciprocal of the derivative of f at f inverse of 2. So what we need is, well, we know what the derivative of f is, and we need f inverse of 2. In other words, we need to know for what x is f of x equal to 2. So we write square root of x minus 2 equal 2 and try to solve for x. We can square both sides and get x minus 2 is 4, and that gives us x equals 6. And indeed, if we plug back x equals 6 in root of x minus 2, we obtain 2. So that means that f inverse of 2 is 6. In other words, f inverse, the derivative of f inverse at 2 is 1 over the derivative of f at 6. So because f inverse of 2 is 6, we plug that in and we obtain that the derivative we are looking for is 1 over the derivative of f at 6. But the derivative of f is 1 over 2 root of x minus 2, so when we plug x equals 6, we obtain 1/4. In other words, the derivative we're looking for, derivative of f inverse at 2, is a reciprocal of 1/4 in other words 4. Now if we turn to the third question, we're looking for a formula for f inverse of x, and we've discussed before how to obtain such formulas. We start with y equal f of x, and then we solve for x, and that corresponds to x equal f inverse of y. So solving for x here means that we're going to square both sides, and we obtain y squared equal x minus 2. But of course we have to keep with that the assumption that y is positive, because on the left hand side y equal square root of x minus 2 imposes that y is a non-negative number. So solving for x, we obtain y squared plus 2 with the condition that y is non-negative. That means f inverse of y is y squared plus 2 for y non-negative. And if we want to go back to the variable x, we obtain f inverse of x is x squared plus 2 for x non-negative. Now we can use this formula for f inverse of x in order to calculate the derivative of f inverse, and it is simply 2x, so its value at 2 is 4. Of course, it's no surprise, we've already calculated it, but you see two different methods to calculate this derivative number at 2. Now, just to see what's going on, we can sketch the graph of the two functions, and as expected, they are a reflection of each other about the line y equal x. Now turn to the next video to look into exponential functions.